Now we're going to investigate a little quirk in dealing with the characteristic polynomial. We're going to figure out what we do when the characteristic polynomial has what are called repeated roots. So an example of this is you have a0 equal to 1, a1 equal to 4, say, and then you have a recursive formula like an equals 4an minus 1 minus 4an minus 2 for n greater than or equal to 2. Now this looks almost exactly like the same situation we had in the last video, but this one has something that's a little bit more uncomfortable. If we look at the characteristic polynomial, we take our original recursive equation, move everything to the left. We notice that that gives us a characteristic polynomial of r squared minus 4r plus 4 equals 0. If we factor out the polynomial, we get r minus 2 times r minus 2. And unlike the other problems that we've worked on, that only gives us one solution, r equals 2. So if we follow the pattern of what we did, we'll say, well, okay, fine, an equals a times 2 to the n. That is a perfectly good solution to our recursive formula. Let's see if that helps us solve the problem that we have here. Now, if I plug in n equals 0, I get a equals 1. We're looking pretty good. I can just put in a equals 1 into my equation. However, if I take one extra step and look at n equals 1, that gives us 2a equals 4. And 2a equals 4 gives us a equals 2. So which is it? Is it a equals 1? Is it a equals 2? Well, according to this one, it has to be both at the same time, which is impossible. So yeah, oops is right. So we have to find a new way of figuring things out, right? So our real problem here is we had two conditions, but we only had one variable to worry about those two equations. Whenever we have two equations and one unknown, there is always a very real danger that we can't solve that equation, that it has no solutions. So we need to somehow get two variables. Well, one way of trying to do that is, okay, fine, a times 2 to the n plus b times 2 to the n. See what happens there. Well, if we factor out to 2 to the n, we end up with a plus b times 2 to the n. If we do the same analysis, we're going to get a plus b equals 1 and a plus b equals 2. And a plus b can't be two numbers any more than a can. So, I mean, that gives us the exact same problem we had before. So, it doesn't work. Oh well, let's try something else. So, we need what I would call a significantly different solution. The fancy pants phrase is a linearly independent solution. Again, I'm not going to hold you to that language. But we would also like to use our old solution to help. Right? We had one solution, 2 to the n. In the old days, we were very comfortable trying to find ways of leveraging our old solutions to get new solutions. Why should this be any different? Well, hopefully it isn't. So you could do a lot of guessing to see which one would work. It turns out that using a sub n equal to n times 2 to the n is exactly what we're looking for. Sounds crazy, but the thing about guesses is it doesn't really matter how you get your guesses. It's just a matter of, do they work? And the nice thing here is we can check to see if it works. So we have if we look at 4an minus 1 minus 4an minus 2, which is the right-hand side of that recursive equation, we can, and that's equal, of course, to 4 times, well, a sub n is n times 2 to the n, and that subscript n shows up in two places. It shows up in the exponent of 2, just like the old days, but it also is the thing that you multiply by the exponent of 2, right? The n is multiplied by 2 to the n. The n is also in the exponent of 2 to the n. So if I'm doing an minus 1, it's now n minus 1 that gets multiplied by the power of 2 and also shows up in the exponent of 2. If it's an minus 2, it's the thing that I multiply by the power of 2 and the thing that ends up in the exponent of 2. And now we just do a little simplification. Well, we played this game before, right? To make it so that there are like terms, I'm going to take that 2 to the n minus 1 and write it as 2 times 2 to the n minus 2. Leave the other one alone. Do a little algebra. On the left term, you're going to get 4 times 2 is 8. Multiply that through the parentheses to get 8n minus 8. If I multiply that negative 4 through the parentheses, a lot of negatives going around, we get negative 4n plus 8, right, because it's negative. And now we combine those like terms to get 2 to the n minus 2 times 8n minus 8 minus 4n plus 8. Do a little simplification to get 4n times 2 to the n minus 2. That 4 is really 2 times 2, which we can then shove in with the rest of the factors of 2 to get n times 2 to the n. And if that looks familiar, that is exactly the formula for a sub n. So we've proven that a sub n is equal to 4an minus 1 minus 4an minus 2. That is actually a solution. So now we can use it just like we did in the old days, right? So now if we have our old sequence, a0 equals 1, a1 equals 4, and our recursive formula an equals 4an minus 1 minus 4an minus 2, our general solution should look like a times our original solution, 2 to the n, plus b times our new solution, n times 2 to the n. So we plug in n equals 0, we get a times 2 to the 0, which is a on the left-hand side, and b times 0 times 2 to the 0, which gives us 0. So we get a equals 1 because 1 is also a0. So on the one hand, a0 is 1. On the other hand, it's a, so a equals 1. If we plug in n equals 1, if we plug that into our formula, we get 2a plus 2b. If we look at what it's defined to be, it's 4. So we get 2a plus 2b equals 4. This is actually an easy one to solve. If you plug in a equals 1 into our second equation and solve for b, you get b equals 1. So when we solve that system of equations, we get a equals 1, b equals 1. We plug that into our formula, and we end up with 2 to the n plus n times 2 to the n. So in summary, we'll have some definition of our initial terms. A0 equals some number c, a1 equals some number d. We have some recursive formula that looks something like an equals constant times an minus 1 plus another constant times an minus 2, just like before. We're still going to guess an equals r to the n. We get our characteristic polynomial being r squared minus the first constant times r minus the second constant equals 0. We will solve that equation and get r equals something. We'll call it r1. So our general solution is going to look like something like a times our original solution, r1 to the n, plus b times our new solution, which is n times r1 to the n. We plug in our initial terms. a0 equals a on the one hand if we plug it into our formula, but on the other hand, a0 equals c, that was our definition. So a equals c, whatever those are. If we plug in n equals 1, we get a1 equals r1a plus r1b if we plug that into our formula, but also we defined a1 to equal d in that first line, and so we set those two equal to each other. Just like before, now we have a system of two equations and two unknowns. We solve for a and b, and then we plug that into our formula. an equals a times r1 to the n plus bn times r1 to the n. All right, so now go ahead and finish that last problem on the characteristic polynomial. That's the PDF file included with this video.